Okay, so we've worked out a great circle distance of 4609.5 from position A to position B. We worked out an initial course, 8902.8, north and west, elevated pole, direction of travel, that's how we named it. We worked out a final course, 4952, south and west, because it was opposite to the elevated pole, still in the direction of travel. That never changes. What we're going to do is we're going to save this value as E for initial course, or this value, 4952.0, as F for final course. Now, the reason we're doing that, the quadrantal value is this angle here, or this angle here. Okay, that's the angle we're working with. Remember, what we're dealing with is actually mathematics, not really sailings. We're just putting it in our own context. So what we have is that great circle there, which we now say, I know the distance, I know the initial course, I know the final course. Now, where's the vertex? The vertex is this mythical point of the highest latitude that we often talk about. So now what we want to do is say, right, where is it? Why do we want to find it? Well, A, it tells us our highest latitude, but B, it also means that we can calculate any waypoint on that course line if we have it, which we're going to cover in another video shortly. So, where is the vertex? Well, the vertex is very easy to find if we just follow one simple rule. The vertex is the highest latitude on a great circle. And when we're at the vertex, our course is either 270 or 090, depending which way we're heading, whether we're heading east or west. So if our course is the highest latitude, if we are going into higher latitudes, we can't be there yet. So for example, I'm at point A here. My course was 271. 271, I'm in the northern hemisphere, heading somewhat north. 271 is therefore taking me into higher latitudes, so the vertex must be more in my direction of travel. I can't have got there yet because I'm still going up towards it. So the basic rule for finding the vertex and naming the D long is look at a course. Any course, doesn't matter. Okay, it's all just relevant to that one point. If the course is taking me into higher latitudes, the D long for the vertex is in the direction of travel. So here, I was heading 271. 271's taking me into higher latitudes, so the vertex must have been ahead of me. I haven't reached it yet. I'm heading west, so if something's ahead of me, it's more west. So the vertex has to be down here. And we can confirm that with the final course. My final course was 229, or 230, call it for argument's sake. It's heading this way. It's going into lower latitudes. I must have already been past the vertex if I'm heading south. Okay, because I'm heading into lower latitudes. The vertex is behind me. I'm heading west, so anything behind me is to the east of me. So the vertex is behind me from position B, or ahead of me from position A. Now, in some exams, like the SQAs, you don't need to do both courses. The rule applies to all of them. We're only sailing on an arc of a great circle, not the entire great circle. So we don't actually care if we pass through the vertex or not. It's just a point we have to calculate for reference of doing other sums further down the line. Once we've got our initial course and final course, it'll be used in order to find those waypoints. Now, in order to do that, we use what we call Napier's rules. Okay, now Napier's rules are two basic rules that we have on our formula sheet. Okay, so you can see there at the bottom of the formula sheet, we have sine of the mid part equals cos of the opposite times cos of the opposite, and the one above it, sine of the mid part, tan of the adjacent times tan of the adjacent. Okay, they are the only two formula for Napier's rules. So what do they mean? Well, the first thing we do is we draw a diagram. Okay. Napier's rules are used when we have a 90-degree angle. In this case, the vertex. The reason we have a 90-degree angle is because at the vertex, our course, as we said, would have been 270. So there would be a 90-degree angle there. We're heading 270, the pole is due north of us, therefore there's a 90-degree angle between our coastline and the meridian above us. If we have a 90-degree angle, we can use Napier's wheel. Okay? If we don't have that 90-degree angle, we cannot use Napier's wheel. There must be to have a 90-degree angle. Now I'm going to call that P2, simply for the avoidance of confusion with the previous P that we had. Now Napier's wheel is a hard and fast rule for making it, and it looks like this, with 5 sections with a little bit in the middle that we write the word complement. Some places you'll see it written 90 degrees minus, it means exactly the same. Okay. Now Napier's wheel is just a mathematical thing that some really clever bugger came up with, and it works for finding angles and sides within a spherical trigonometrical right angle triangle. And the way we do it is quite simple. We need the vertex to do anything here, or the 90-degree angle. In this case, it is the vertex. We put that at the top. The bit at the top here, that vertex, that is the 90-degree angle component of the triangle. Okay? So a triangle will always have 3 sides and 3 angles. The 90-degree component, whatever it is, goes at the top. And then the only rule is you have to go continuously in one direction around it, keep going in the same way, and alternate between side, angle, side, angle, side. So the vertex is here. It's an angle. So now what we have to have is the 2 sides that touch that angle touching that part. So we'd have PV here, and then we'd say, right, okay, what was the next angle after PV? Well, it was angle P2. Then the next side is side PA. Then the next angle is angle little a. And then the next side is AV. As I said, you need the 2 sides either side of V touching it. So the adjacent sides to angle V are PV and PA, and AV, sorry. So we put them there. If we took little angle A, the 2 sides touching it would be AV and PV. AV and PA. So there's AV and PA. Angle P2, we've got PA and PV either side of it. PA, PV. And it works with the sides. There's the side PA, the angles are little a and P2. There's the side PA, the angles little a and P2. We just start at the vertex and go either clockwise or anti-clockwise around the triangle. Side, angle, side, angle, side. Angle, side, angle, side, angle, side. We just continue with that. And it doesn't matter if you go clockwise in the triangle and anti-clockwise in the wheel or vice versa, you can go the same in both. Makes no difference. Okay? We're having side, angle, side, angle, side. So, we've got 2 rules. Sine of the mid part, cos of the opposite, tan of the adjacent, tan of the adjacent. What does it mean? Well, it literally means the sine of the part in the middle between 2 adjacent parts can be found by timesing the tan of that part and the tan of that part. So if I said PA was the mid part, the sine of the mid part here is the tan of this part times the tan of this part. That's all it means. When it says cos of the opposite times cos of the opposite, it literally means to find the sine of this part in the middle of the 2 opposite parts, we cosine them. The important thing for doing this, just like any wheel, when we come to use it, we take off anything that's stabilizing it. Get rid of that vertex at the top. We're not going to consider that mid part. Okay? So in other words, if we said PA was the mid part, the 2 adjacent parts would be A and P2, and the 2 opposite parts would be AV and PV. Adjacent ones are touching, opposite ones are not. So if I said P2 was the mid part, PA and PV are touching, so they're adjacent, because they're adjacent to it, and AV and A are opposite. That's all it is. Okay. Now what we do is we look and say, right, what parts of the wheel do I know? Well, thinking back to the example we've just done, I knew PA when I started the question, and I worked out the initial course. What else do we know in the wheel? Well, we don't actually know P. I've called it P2 to differentiate it, because the original P of 5845 that we had on the example a minute ago for distance there was all the way from A to B. Now we're just talking about the vertex. If I find P2, I know the longitude of this meridian. If I find the longitude of this meridian, that D long will tell me between the two. If I know that longitude, or D long, sorry, and this longitude, I can find what this meridian is. So if I find P2, that will help me to get the longitude of the vertex. 90 minus A gave us PA. So 90 minus PA will give us the latitude of A again. In exactly the same way, 90 minus PV would give me the latitude of the vertex from the equator. So if I can find PV, that will get me the latitude. AV is the distance along this arc from A to the vertex. So that is the distance of A to B. If the question asks you to find the position of the vertex, we're going to have to find PV and P2. If the question asks us to find a composite great circle distance, for example, we'd be finding AV as well as another. So what we're going to do now is just work through an example of finding the latitude of the vertex. Okay. So what we do is we say, okay, sine of the mid part. And I don't know which bit I'm using yet. I need to look at my formula. I need to find the latitude and the longitude. So I'm going to start simple and just go for the bits where I can make the bits I need the mid part. The latitude. I said if I want to find the latitude, I have to find PV. If I make PV the mid part, PA and A are directly opposite, so I can just jump straight in. So sine of the mid part equals cos of the opposite times the cos of the opposite. Now, that means the sine of PV equals the cos. It's touching this word complement below this line. Above this line, they stay as themselves. Below this line, we call them complements. Okay. Now, what that means is it's 90 minus the original number. What we can do, though, is simplify. If you picked a random number, say 40 degrees, and you did the cosine of the complement of that, that would be cos bracket 90 degrees minus 40 degrees. Close bracket equals, get that number on your screen. Now 90 minus 40 was 50. If you just do sine 50 on your calculator now, you'll get exactly the same answer. Sine and cosine curves are 90 degrees apart. So whenever we have the cosine of the complement of something, we can just change it to the sine of that something. So the cosine of the complement of PA, we can just change that straight away to be sine PA. The cosine of the complement of little a, that can just become sine little a. Similarly, if we had sine of the complement of something, that would just become cos. Okay, so sine comp, if it was, for argument's sake, sine comp little a, we could just change that to cos little a. Okay, so sine PV equals PA was 40 degrees 10 times sine of little a was 8902.8. Now, as I just said, we've already got these in our calculator memories. We have PA as A in our calculator memory. We have little a as E in our calculator memory. And it's for this exact reason I call it little a, not A. Because if you keep calling that A, and you're using your calculator memory, so you're going to do sine PA times sine A, and you're going to do sine recall A times sine, and you stand a chance of doing recall A again. Okay, which is going to give you the wrong number. If you're not on the ball, you'll not notice that. So, when we do that number crunching, the sine of PV, we just use our calculator memories. Okay, and on our calculator, we're just going to do sine recall E times sine recall A equals, it comes out as 0.644923936. Sine minus 1. Means that PV equals 40 degrees, 0.9, and it's 35.9 seconds. Okay? And that's 35.9 seconds, which I'm going to call 40 degrees, 0.9.6 minutes. Okay? You'll see in a moment why I've wrote both values out. It's just to explain the next step. Now, that's my PV. Okay? That's from the pole down to the vertex. PA was 90 minus the latitude of A. And if I done 90 minus PA, I'd get A again. So this time, what I'm going to do to get the latitude equals 90 degrees minus PV. Which is 90 degrees minus 40 degrees, 0.9.6 minutes, which is going to be 49 degrees, 50.4 minutes. And that latitude would be the same in both the northern and the southern hemisphere. So I'm looking for the northern vertex in this case, the one I passed through. We call it north. Okay. And that's how I find the latitude of the vertex. Just find PV. To get the longitude of the vertex, I need to find P2 now. Okay. So what I'm going to do is say sine of the midpart equals, got a problem now. I've worked out PV. Did I do it correctly? Well, I could use that as an adjacent and that as an adjacent, but if I've got it wrong, it's going to compound the error. Now, yes, I might have got the initial course wrong and this whole wheel's wrong, but if I use that number after I've used that number wrong and carried it through, I'm now carrying another wrong number through and compounding my error. I'm going to lose more marks than doing it a slightly different way. And the other option is, let's forget I've worked out PV. The sine of PA as the mid part is going to be the cos of this part and the cos of this part. Sorry, the sine of the complement of PA is going to be tan, not cos and cos. So, if I made PA the mid part, then the tan of this times the tan of this would give me PA. But if I already knew PA, I could transpose it to find that. If you think about it, if I said the value of this part was 6, okay? Now I know it won't be because of sine and all the rest of it, but let's say the sine of this mid part was 6. That would have been the tan of the adjacent times the tan of the adjacent. So 6 could have equaled 2 times 3. If I wanted to find that part, I would have done using 6, 2 and 3, 6 divided by 2 to get 3. I would have just transposed that equation. I'm going to do exactly the same now. So sine of the mid part is tan of the adjacent times tan of the adjacent. So sine of the mid part being PA, complement of it, comp PA equals tan, but it's the complement of little a times tan of the complement of P2. Sine of the complement of something we said before became cos, so it's cos PA equals Oh, hang on. Sine and cos we just swap. Tan has to become cotan. That becomes 1 divided by tan little a times 1 divided by tan P2. So sine the complement of something becomes cos of it. Cos the complement of something becomes sine of it. Tan the complement of something becomes 1 divided by it. Okay. So that means cos PA equals, and when we multiply fractions, we just do the top times the top, the bottom times the bottom. If you think, if you had half a cake and you halved it again, you'd have a quarter. 1 over 2 times 1 over 2, 1 times 1 is 1, 2 times 2 is 4, you've got a quarter. So that becomes 1 times 1 is 1. Tan A times tan P2, you can't really do anything with that. You're just going to end up with tan A times tan P2. Oh, bugger. I want to find P2. If I want to get rid of it off this side, I'm going to have to multiply it to get it over here. And then it's going to be tan P2 times cos PA. It's going to be 1 divided by tan A. And I need to get this cos PA from this side, so if it's multiplied over here, I'm going to divide it back over that side. What I end up with is just swapping tan P2 and cos PA over. Tan P2 equals 1 divided by tan little a times cos PA, which equals 1 divided by tan 89 degrees 02.8 minutes times cos 40 degrees and 10 minutes. Okay. Which means tan P2 equals, so we do cos we call A times tan we call P. You want to write your calculator memories in underneath so that you make sure you times the cos and the tan correctly by the correct component. We don't want to do tan A or anything like that. So cos we call A times tan we call A equals 1 divided by that is the easiest way to do it. You wouldn't need brackets on the bottom if you didn't. That means the tan of P2 equals 0.021775665. Shift, and it's tan P2 equals, so P2 equals 1 degree 14 point, and we can call that 0.8 minutes. Now that's the D long, that's this angle here. We said before, our initial course, which is the position here, which is the position we've used for this wheel, you could have done it all with B and done BV, little b, and PV, and use the longitude B here, but we've done it with A. Now our course was 271. We were heading slightly north. We said if we're going into higher latitudes, D long is in the direction of travel, so that's going to be west. The longitude of A equals, was it 5 degrees 15 west, 005 degrees 15.0 minutes west. So the longitude of our vertex is going to be 006 degrees 29.8 minutes west. And that's how we do it. Now there is an alternate way, which I'll do on the board in a different colour, because although it is good and it is quicker, it's also prone to errors. Okay, because there's a couple of rules. The other way is saying I'm confident that PV was correct. So I'm just going to do sine of the mid part, tan of the adjacent times tan of the adjacent. So what we do is we say, right, sine of the mid part equals tan of the adjacent times tan of the adjacent. Say, okay, sine of the complement of P2 equals tan PV times tan of the complement of PA. So that becomes cos P2 equals tan PV times 1 divided by tan PA. Tan PV is itself, it's not a complement. The number 2 is itself as well, if we use that as an example. If we want to cross multiply these fractions, tan PV, anything that is itself, is divisible by 1. The number 2 is actually 2 divided by 1. We just never write the divided by 1 because that would be a bit stupid. Okay? So, to multiply it, it would literally become tan PV divided by tan PA. Okay? So cos P2 equals tan PV divided by tan PA. And if you put those numbers in, you will get slightly different answers to what it should be. And the reason for that, we're using a wheel. Let's imagine this is an analogy of a real wheel for a second. We put a chock on it to build the wheel and create it. When we came to use the wheel, we got rid of that chock. Okay. Every time you take a chunk out of a wheel, it will wobble a bit. You'll buckle it. Yeah. Think of every time you've curved your alloy wheels in your car or something like that. They put the little weights on them if they're damaged, or even when they're made because the tolerance is in it. They put little weights on it to balance the wheel. Every time we take a number, we carry it forward. If we rounded it all, we're taking a chunk off that wheel. We need to balance it. The way to balance it is to use PV to the infinite decimal place. You'll notice I wrote it out as 400935.9, but I applied 09.6. That's because units we work to is 1 decimal place for latitude and distance. But if I'm going to carry that number through, I have to use that infinite decimal place. Okay? So if I do this method, I must do the tan of 40 degrees 0935.9. I cannot round it to 9.6. Now, in this example, because they're so close, that's only 0.1 of a second away from it, it will make virtually negligible difference. But as it gets further and further through, you'll see you'll not always be 35.9. If that was 33.1, we'd have rounded it up from virtually halfway. So that would make a greater component of error. Okay? That's the reason we use the infinite decimal place. And PA was 40 degrees 10. So if you do tan of 40 degrees, 9 minutes, 35.9 seconds divided by tan equal A equals, you get cos P2 of 0.999762977, but P2 again comes out to the infinite decimal place the same, 1 degree 14.8. And if you look, the seconds are even exactly the same, 51.01. Again, we were still heading west. The longitude of A was still the same at 5 degrees 15. So we get exactly the same answer. Okay? So you can do one way or the other. People prefer this way because it's simpler to do. You're not having to transpose that. And it's not the nicest of formula to transpose that. But the risk is, if you've messed up your PV value, you're going to carry that error through. If you say, well, I've got it wrong because I messed up A, fine, you did. But you've used the same level of accuracy of the error here, you haven't compounded it through, knowing that you could have made the situation worse and worse and worse. And that's how we get the latitude or longitude of the vertex. Good old-fashioned Napier's wheel. And once we've done that, now we know the position of the vertex. We have that position labelled on our diagram. We know what it is now. It's now a known component that I can use to do calculations with. Okay? I can do any calculation I want with that now to find any position on that great circle leg or the other side of it, or even not between my points. Any point on the surface of the Earth on that great circle, I can now work out the exact position. And that's one of the benefits of working out the position of the vertex. Examiners are happier with this way because it's less of an error risk. Students are happier with this way. It's up to yourself if you want to take the risk. Completely honest, 95% of students prefer this way, and it will help you for passing an island and things like that, because that's the way you would do it. And for composites, that's the way you would do it. So, because for composites, you don't know little a, for passing an island, you don't know angle x, is what you're going to call it. So this way tends to be more beneficial to the students for doing the same thing on different calibrations. But that way is the way the examiners prefer you to do, because it's more mathematically liable to be correct and less open to any errors.